Hey, all, today we are going to continue talking about regression and linear regression, linear models, and we're going to use the same example from the last lesson. So if you've saved that data, that's great. If you haven't, I have it here again. So I will just take a moment to put these two lists into your calculator. You can see I already have the linear regression output, but we're going to need them as we go. So go ahead and take a pause here, put those in, and then come on back. So when we did this linear regression, we have talked so far about A and B. A is the y-intercept of my linear model. B is my slope. And I realized when I put my data in last time, I did have an error in my input. Oops. In my list 2, my first data point was wrong, so I apologize for that. So if my information looks different than it did last time, it's because I went and I fixed that. So we have that slope. The ideas that we talked about were still the same. We just had the wrong value because I wasn't as careful as I should have been. We get an R. That's our correlation. It's negative. That doesn't mean it's bad. It just means the line goes down to the right. 0.94 is pretty strong. It's almost -1, which would be a perfect relationship going down. So the new value we want to talk about is r squared. When we refer to r squared outside of the calculator, you can see here I've titled this with a capital R. That's because r squared should be a capital R. It's quite literally the correlation coefficient squared, but we use uppercase R. That's just a notation thing. I don't know why there's no uppercase R in the calculator, just an output thing. And so this thing's called the coefficient of determination. It is a percentage, so we're going to say that our r squared value is 89.14. I'll do 2 decimal places there, percent. Like I said, it's literally the r value squared, and then we convert it to a percentage. And this is a value that lets us know how much of the variation in the price for these Toyotas. Remember, we're talking about Toyotas, 250 miles from Redlands, California. How old they are and how much they're listed for. This 89.14% tells us how much of the variation in price that you would see. So you're going to go on and you might look at these Toyotas and you might find even more, and the prices aren't always going to be the same for the same year vehicle for different reasons. But 89.14% of the variation in that price we can attribute to the age of the car. So the age of the car has a pretty large influence on the price that it will be advertised at. So let me pause here. I'm going to write up how I would say that, because this is going to be something we need to learn how to do. Say and interpret this r squared value. We can almost write these interpretations in sort of a formulaic way. We can write it this same way every time and just sort of input the context of our problem. And so I would say that approximately, because we don't know guaranteed, this is just based on the small data set we have, approximately 89.14% of the variation in the price of Toyotas. Again, prices vary. We don't list things for the same price just based on the year every time. These prices are going to vary. That's the world. Things vary. It's not always nice and neat. We can say that approximately 89.14% of the variation in the price of these Toyotas can be attributed to, sometimes you might say, is accounted for by the age of the car. And so this can be sort of a plug-and-play situation. If you like formulas, we can write essentially the same thing every time. Fill in the blank there with r squared. Fill in the blank there with your response variable. Fill in the blank there with your explanatory variable. So we can sort of plug and play here if that makes this simpler, because sometimes the language of this can get a little tricky. So there's like about 11% left over of variation, and so what that could be attributed to, we don't exactly know, but that would be sort of things like, was the car in an accident? Does the car have rust because it was owned in a place at one point where there's snow? Um, were there modifications done on the car? Things like that. Another thing we'll look at to make sure that our linear model is a good model, we always want to check to make sure that it's appropriate for us to have modeled the relationship using a linear model and make predictions. And so we will look for outliers. We want to look at the shape and make sure it's linear, but sometimes there's things we don't see. And so we could look at a plot of the residuals. So we calculate residuals by subtracting what we observed minus what we would have predicted for the explanatory variable. And so we can do that for every data point. We can find a residual for each data point, and then we can plot those residuals. So in this first scatter plot, we had we plotted the year versus the difference in the men's and women's age. I believe it was for marriage. And so then we went and calculated the residuals, and we plotted those residuals against the original explanatory variable, and we get a different scatter plot. If we want to use a linear model, and a linear model is appropriate, our original scatter plot should look like it has a linear pattern, which it does. It should not have any outliers, which it doesn't appear to. When we look at the plot of the residuals, we should see no pattern. Maybe counterintuitive, but when we're looking at a plot of the residuals, we want to see that there are no patterns, that this is sort of this just sporadic display of data points, which in this case is. If we were to see some sort of curve in our residuals, we might go reassess what our actual trend was in the original scatter plot. If we saw something where perhaps we had this sort of like fan effect, where we had, or a funneling effect, where we had a bunch of tightly packed residuals, and then it sort of fans out like this in some sort of pattern, that would make us concerned with whether or not our linear model was good. So if it's always good to go ahead and look to make sure, like, let's make sure that our linear model is appropriate. Let's make sure the predictions we are making are things that we can do soundly. And one way to look at that is by looking at the plot of the residuals. We will, in class together, go through the calculator process of how we can actually calculate residuals and create one of these scatter plots pretty easily without having to do a bunch of calculations by hand. And the last thing we want to look at when it comes to looking at these relationships, these scatter plots, is the different types of points that might appear that we should pay some attention to. So outliers, points that have leverage, and then points that we can consider influential. And so an outlier is a point that has a large residual. And large, we would say, relative to the rest of the data set. So if I look at this first scatter plot, we have this point hanging out up here. A large residual is a data point that is far above or below the rest of the data. That one certainly is far above the rest of the data. And so we would call that an outlier because it has a large residual. I think we would call that point an outlier as well. A point that has leverage, it's a point that is far from the rest in the x direction. So in this first one, that that data point does have a large residual, but it's not far away from the rest of them in the x direction. It's sort of like in the middle. But if you look at the second one, that data point, which doesn't have a large residual, because if we were to graph our linear model, it would look like this. It would almost go through all of those points, including that point. So it's not an outlier, but it does have leverage. It's far away in the x direction. And then most of the data here looks like it has this linear trend, and then we have this one that's way over to the right, so that one does have leverage. And then lastly, a point that is influential is going to change the model if we remove it. So it will change the equation if we remove it. So if we look at this middle one first, that point, like I said, pretty much follows that trend, and so this one would not be influential. If we take that out, our line that gets graphed is going to be about the same. If we look at this third one, this one is very influential. Without that data point, this is the trend that we would see. That would be the linear model that we would graph. With this point that has a large residual and it's got leverage, it's going to make our line look something more like that, drastically different. So we would say this point is influential. And then finally, if we look over here at this one, no leverage, it's an outlier. It probably has some influence because our line would probably be just like that without it. And this data point is going to probably pull it up a little bit. And so it's going to have some influence, but not nearly as much as the one in number 3. So we've talked about R squared, we've talked about residual plots, and now the different types of points and how they might influence our linear model. Please, if you have any questions, ask. Make sure you watch the end and answer the questions at the end. As ever, if you need help with those, ask me. Take your time on those, and good luck.